Lab 3 black hole Phys2211. So the purpose of this lab is to calculate the mass of a black hole using a star trajectory that we will map out using glow strip. And the second part of the lab is to determine initial velocity that's needed for imaginary scenario, and we want to determine the velocity needed for a spaceship to escape the black hole without crashing to withstand the force of the black hole. And some of the fundamental principles that we'll be using are Newton's second law and the universal law of gravitation. And this is a preview of our results. So Newton's second law is basically says an object that is in motion or at rest will stay in that state of motion unless acted on by external force. And this is the way of saying the rate of change of momentum of a body over time is directly proportional to the force applied to that object. This is also known as the momentum principle. And the law of gravitation, which is another important subject in this lab, it describes attraction between two objects, and it is equal to the gravitational constant, which is 6.67 times 10 to the negative 11, times the product of two masses over the distance between the two objects squared. We also looked at the two update formulas, position velocity formula that we've been using so far in the course, and that allows us to determine the change in object position velocity over time. So we also know that the net force of an object as acting on the object, of course, you go to the change of momentum, and we decide we can actually split these this net force into the perpendicular component and the parallel component. So the perpendicular component represents the change in direction of the object and can also be thought of as a centripetal force in the circular motion, and that's equal to mv squared over r. Parallel force, however, determines the change in magnitude of momentum. So this directly affects the acceleration, the change in net force of the object, and that's equal to change in momentum over time. And then finally, because gravity from the star and gravity from the star and gravity from the black hole are the only really present, we know the force of gravity equal to the net force. Um, Part one, black hole is system, and planet and ship are the external objects. So we set these initial conditions according to what we know, and our objective is to analyze star's motion to find the net force on a star for all points in the data set. So that's exactly what we do here. We set the initial conditions, we find the change in momentum, and then we know that F net equals the change of momentum over time. So we use Newton's second law to calculate um, the parallel component and the perpendicular component of the F net force. And then we rearrange gravity equation to solve for the mass of the black hole. And using that, the results we get are for the mass of the black hole is 1.6378 times 10 to the 34 kilograms. And these are the other results we get for the perpendicular component and the parallel component. We add those together to get the net force in general. So for part two, we'll find the initial velocity of the ship. The ship, the system, the black hole, planet, and universe are the externals of the system. So we set these initial conditions again, and some of these initial conditions are actually using what we got before for the mass of the black hole and everything. So we're using that. We use the mass of the black hole we got from part one as the initial condition for part two. And to find the velocity of the ship, we first find the net force acting on both the spaceship and the planet. Once we find the net force acting on the spaceship and the planet, we apply the velocity and position update formula to both of them to get arrived at the answer that we want. Spaceship initial velocity is equal to this vector right here, and the closest distance between the ship and a black hole is 4.36 times 10 to the 10 meters. Some of the sources of errors could include fact of rounding errors for both the parts, and for part one specifically, we may have needed a greater time interval needed for the star's trajectory. Any of the errors we encountered in part one could have also affected the velocity of ship calculation part two, because we use the mass of the black hole from part one to part two. And there's also some glow strip errors that could occur with calibration and initial conditions for the simulation. The first discussion follow-up, to answer this question, we need to understand like net force is the change of momentum over time, and we know that because of the definition of the second law, Newton's second law, we know the parallel component of net force is equal to the parallel component of change of momentum, and same applies for perpendicular components. So parallel components are responsible for acceleration, and perpendicular components are responsible for change in directions, because these they actually are equal to each other, component of net force and perpendicular and change of momentum. And the final question is, what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? So we want to model velocities around the planet because the planet, of course, is able to maintain its orbit around the black hole. And the ship's velocity, we want that to be close to the planets, but we want the y component velocity to be larger and the x component velocity to be smaller and negative, because we want to make sure we want to avoid colliding with the black hole. And this little picture here kind of shows the results of choosing those types of velocities, right? And we also increase the time frame so we get a better glimpse of the orbit. And after we kind of mess around with this, when you run the simulation, you can kind of get the results of what the plot velocities could be. Yeah, thank you for that.